Retrieval and external memory.
On nothing.
Nothing.
Okay. Good. I think it's okay. Yeah. All right. So this is an external memory data structure kind of paper. It's based on my joint work with my student Sharma, Jeff Witter, my postdoc advisor, and our collaborator Cheng Cheng, and builds on our line of work in top K document retrieval. All right.
I didn't realize Jeff was still doing research. Is he still?
This is a journal paper, you see.
Is what?
STALG is a journal paper.
Oh, okay.
So it comes like 6 years later.
Oh, okay.
No, but he's still submitting papers.
I know. He's just running universities and stuff like that, right?
No, but he's still writing papers and he's still submitting to Stock and Fox, which are not going, but still. I mean, he did. Hey.
Okay. I thought he was bureaucratic, purely.
No, I think he was. I feel he was too simple for being hard bureaucrat, I think. So anyways, so what is the problem? So we start with pattern matching. So what is the fundamental pattern matching problem? Given a text T, we have a pattern P from some alphabet sigma, find all the locations of pattern P in text T. And then we see this problem not in algorithmic sense, but data structural sense, where text T is already given to you, you build a data structure, and then you find where the pattern occurs. So standard data structures are suffix trees and suffix arrays, right? So now this document retrieval problem, which was introduced by Muthukrishnan in SODA 2002, it says, okay, the text is now collection of documents or strings, which are D1 through DD, so D documents, and output all the documents which contain pattern P. So not all the output locations, but only all the documents. And number of documents may be much lesser than number of occurrences of the pattern. So the problem becomes interesting. Muthu gave like kind of optimal linear space structure doing this query in linear time. So in external memory, this problem actually converts to orthogonal range search with one of the dimensions, it's a two-sided query, so bounded below and bounded above, and one of the dimensions, it's an open-ended query, so it's only bounded below, but not above. So it turns out, all right, so what was the new thing? So now we want to put some relevance score for a document. For example, if you have a pattern P, and if that pattern P occurs more times in that document, then document is highly relevant to that pattern. And now the idea is, okay, give me top K highest relevant documents based on this, okay? So it could be frequency is one of the popular measures, proximity or just static weight are there. Now there is also some relation between threshold queries and top K queries. So typically when you say top K in one of the dimension, you are saying, okay, give me top K, versus threshold means in that dimension you are asking, give me everything above this threshold. Okay, and both are connected. Typically they have the same complexity.
So do people consider relative frequency as well? Like if the documents are different sizes, right? So I could have it appear 10 times in a million words or 10 times in 100 words. Do I care?
Yes. So TF-IDF fully can be done also, and yeah, you can do these things. Yeah. All right. So again, there are suffix tree based solutions for this, and that's what Muthu also had. So we gave this solution based on suffix tree. So if you look at this string banana, standard string urban, which matches with banana quite a bit, and you make a suffix tree out of it, and at each leaf, you write which document that leaf string comes from. So here in this thing, right, every root to leaf path corresponds to one of the suffixes, and then at the end of that leaf, you annotate what document it comes from, right? So now if AN was our string, then this becomes, then this becomes the locus. And then within that subtree of locus, you find, okay, D2 occurs once, D1 occurs twice, and that's why D1 is more relevant. All right, so our framework to answer these queries was something like this, okay? So you look at the tree, and each of these leaves of this tree have labels, right? It's which document they belong to. So now what we do is we go document by document. So let's say we go to D1. So if this leaf is D1 and this is D1, then we also make an entry for D1 here and make these links from leaf D1 to this particular node and this to this particular node. And then since this is also D1, so you take the LCA, that is least common ancestor, of this point and this point, which is here. So you make links from here and here. So you make this kind of an overlay of links. And this overlay, so these links come from each document, and you make this kind of an overlay. So for example, this would be overlay for D5. And these are the links.
That's another basic question. So if the same word appears multiple times in one document, you just have weights on these leaves? Like if banana occurs 10 times in
Yeah,
D3.
so no, not yet. Not yet.
Not yet.
So this is one, right? So this link has one, this link has one. So I'll show you the weights. And then this one will have two.
No, but the whole thing's a suffix tree, right? So
Yes.
if I have, like each leaf corresponds to some suffix, right?
Yes, some suffix, yes.
And if that suffix occurs multiple times in the same document,
That suffix will not occur multiple times in the same document. The suffix, it's a generalized suffix tree, and so suffix occurs only one. Pattern can occur multiple times. So this particular suffix will only occur one time.
There's always an end of file character.
Yeah, there's a dollar character at the end. All right, so we annotate this by these links. And now what we do is for each link, right? I write where does it start from, where does it go, and this is the frequency. All right, so this link particularly corresponds to frequency of 2 because there is this D1 and this D1. And it starts at node ID 3, which is the pre-order ID, and it goes to node ID 1, which is again the pre-order ID of the root. So just put it like, so these links basically have the starting point, end point, and its frequency, or any other measure. Okay? And then what happens is that if my locus, if my pattern matches here and this is my locus, then what I'm interested is how many links come out of this subtree and go above this subtree. Okay? And out of those leaves, who are the highest, who has the highest weights, so highest scores, which is this. Okay? So this is what I look for. So now, for example, this subtree, right? Subtree of V starts from 19 to 3, and top K are D6 and D5. Top two links are that. So you will see that there is a link for D5 here, which has 3. And then there is a link for D6 here, which has score 4. All right, so how does this query convert? So query converts to a 4-constrained query. Origin greater than 19. Origin also less than 37. Target less than 19, so above this. And score above 3, for example. Okay? So if I could take the threshold version of it, it is basically score greater than or equal to 3. So this converts to 4 constraints. Okay? I can also change a little bit and make this target less than 19 into target depth less than 2. So I can make it a little bit. But what happens with 4-sided? So there are 4 constraints to this query. So when you go to external memory, if it is a 4-sided query, the answer is, okay, good structure may not exist. For example, if you have just a two-dimensional 4-sided box, rectangle, then it will take n log n over log b amount of words. So the structure is like almost n log n sized. So that's a log n size blow up. However, if it is just 3-sided queries in external memory, then it's doable. So then you can kind of get optimal bounds, linear space optimal bounds for query. So what we convert this problem onto interval stabbing with priority. So now if you have a linear intervals and you favor interval stubbing with priority, that is an okay problem. It's like a 3 constraint problem, and it can be done. But here what happens is that we are taking these intervals on tree. So that is how we converted this to this thing. And what we saw that earlier also, that it's a 4-sided, there is a 4 constraint to these queries. But then we saw that one of them has the shared constraint. If you go back, if you look at here, so target is less than 19 and origin is greater than 19. So this 19 as a number is shared. So this is not independent 4-sided query, but it has something shared. Okay? So we were looking at what can we do in various formulations with this problem. So there are 3 different formulations and 3 different related problems which can solve this problem. So first is just take shared constraint. Okay, so just exploit the fact that your two queries, two dimensions have the constraint which is shared. So A is equal to C. So this is your X dimension, this is Y dimension, this is Z dimension. But then this A and C are same. So if you have this, then what we gave was order of n log n words, not n log n, but log n. And then optimal IOs with this. Another formulation was a colored or categorical range maxima queries. So in this case, there are points in 2D, and they have colors. And what you do is you are required to report in the range. So this is the X range, okay? Highest Y value of each color being reported, okay? Again, we gave a structure for this, which is n log star n space, and then optimal IOs. What I'm going to briefly show in this talk is just tree interval stabbing with priorities. And again, we get n log star n space, and with this optimal IOs. All right? So let's skip this, I think. So what do we do? Standard, yes?
Just a constant number of colors?
No. D colors. D is a document, so there's a D number of colors. And there are solutions where also D becomes important, but for us it doesn't. D can be bounded by n. Right? So what is this? This is so we first do a path decomposition. So remember, we want to do interval stabbing problem on tree. So we do a path decomposition of tree. So what is that? So take every node and look at its child which has maximum number of leaves. Okay? And go towards that. And now here, look at its child which has maximum number of leaves. So it's not this, it's this. So go towards this. All right? And make this path, which is called sometimes heavy path or sometimes centroid path, make this path. And then remaining part of the tree, you recursively get other paths there. Okay? So this is the path, centroid path decomposition of the tree. All right. Now we want to still steal one constraint out. So here's a trick. It looks like a trick, but we went through a lot of things and cleaned it up to this trick. So we are going to label the node IDs. So what do we do in this case? The visit own centroid path at the end. All right. So we are going to do pre-order labeling, but we are free to rearrange children, and we only rearrange so that the own centroid path comes at the end. So for example, now 1, I go to 2. I don't go here. I go to 2. Now from 2, this is the path. So I'll not go here. I'll go here to 3. Right? Now 3, I don't have any choice. So I just go to 4, and I fill up all the IDs like that. So once I fill up these IDs, what next happens is that there are few properties of this thing. Okay, so pre-order rank, instead of pre-order rank, as I had in the earlier slide, this is now centroid rank. So a good property is something here. So this property is true for even pre-order rank, but good property is something here, which is let node U be a proper descendant of node V on same centroid path. Then each descendant of U, which is this, has a larger centroid rank than all descendants of V except those in subtree of U. So this comes at last if I look at this subtree. So what does this do? It actually allows us to steal one of the constraint out. All right, so because range, we had the range constraint earlier, which is two-sided constraint. Now it just becomes one-sided because we are not going to worry about that. All right, so What happens now? We have to find top k highest code length, which is subtree of locus, and depth of target is depth of locus. So we now categorize these links into two things. Either the links are within the path, which are called co-path link, or links which go across paths, okay, which are called interpath links. Now, another property of the centroid path decomposition, sorry, I forgot to mention, assuming everybody knows, is that number of paths, from any leaf, if you go to root, number of paths you jump is only log n. Okay, so that is one good property. So based on this, what we do is for interpath links, number of paths is only log n. Okay, so based on, we store this in all the paths above, and this log n comes because I'm going to now search log n different structures. Okay, and with copath link, now I got rid of one of the thing, right? So then I can just do interval stabbing with priorities, and that gives me this. And I do a slightly different variant of centroid path decomposition, which is good for external memory, and based on that I get these many IOs. Not optimal at all. The base here is not B. So what do? We do bootstrapping. So if k is greater than b log n over b, then that is optimal number of IOs. But if k is less than this, then what do? We choose g as a grouping factor, which is this factor. Then we group all these things by g, all leaves, and then mark all the LCAs, least common ancestors, and their LCAs, their least common ancestors, and so on. So number of marked nodes is going to be n over g. And then each marked node has something called a fringe tree. Let me show here. Okay. So this part, so if this is V is a marked node and U is its parent marked node, then this whole part is called the fringe part of V. So what we do is within V, we explicitly maintain what are the top k. And for this part, we can recurse again, right? So when we recurse, we get O of log n over B plus kb. Again, still not B, but we converted log n over b to log n over b. So you can see where it's going now. Right? So then we keep doing it recursively. If k is bigger than this, then this is optimal. If k is less than this, another round of that. And then we go down to log n over b additive IOs. So if we keep going down, our structure becomes n log star n space, but gives optimal IOs. Or you can stop at this point, then you'll have this additive term in query, and you can claim linear space. So we get that. This, actually, when I presented this, I claimed this, that it is the new result. And it was the result of categoric thing. But it never worked out. This worked out to alpha cube, and then we said, okay, maybe there is something bad there. So we claimed that result as also log star. That was the other result using colored queries. But yeah, so that's where it stands.
So again, so one of the tricks you're using is that if it's a, whatever you call a copath arc, those paths are just linear, right? So so that's why you said you're able to just use a stabbing algorithm, because you basically just have
add to that fact that numbering. That numbering is also important. The way we do
how's the numbering important?
Pre-order ranking. Yeah, so
special number.
So what happens here is that when we say, okay, let's say this is a locus 13, and when we say that, okay, we are looking for anything which goes from here to here, so then we say, okay, this is 13's subtree. So we say, okay, from anything from 13 to 17 I'm going to consider, which goes here. But the fact is that this becomes two-sided constraint. Then in that case, this 13 and 17 is a two-sided constraint. But if I have like this, this way, then I don't have to worry about this 17 constraint, because that automatically builds in. because this anything on the path is going to be at the end. So I don't have to worry about the right side constraint. Yeah.
Am I right in thinking that the open problem is order and space and optimal IOs?
Yes. Yes. I mean, I don't know. This is maybe Google was kind or unkind, or Jeff was kind or unkind to me during this. But it seemed like, okay, here's this interval stabbing problem on the tree. And it sounds natural, right? Somebody must have done something about it, but we didn't find anything. So yeah, there are variations, there are things, but yeah, not that suited our document retrieval.
All right, let's thank the speaker.